Okay, so this video is about the introduction to electromagnetic radiation and some calculations that we do. So electromagnetic radiation is the energy all around us, but that it's created by electric and magnetic fields. So all of the common forms of energy and light that you know get lumped into this. So all of our visible light, X-rays, microwaves, radio waves, television waves, all kinds of things that you're familiar with, maybe some that you're not familiar with. Visible light's the only thing that we can see with our eyes, but the other stuff is all around us. So electromagnetic radiation gets characterized by wavelength and frequency. That's how we differentiate between the different types. So there's a scale of electromagnetic radiation, and so you can see up here all the different types of electromagnetic radiation that we have. But wavelength is one way that we define or describe the radiation. And wavelength is literally the distance. It's a distance between one point on one wave and the same point on the next wave. So if you imagine these as waves, think about the ocean. A wavelength would be peak to peak. It's the actual distance. Or you could do valley to valley. Or you could do middle to the middle. Those are all wavelengths. So it's the spot on one wave to the same spot on the next wave. And so this gets measured in anything that we use for distance. So we can use meters, nanometers, inches, yards, feet, miles, whatever. So the other thing that we use to describe this radiation is called frequency. And so when we use frequency in our daily lives, they ask you the frequency that you used to attend school. You would say 5 times a week or 6 hours per day. Or 180 days per year. But it was always something per time. A frequency is how many per time. So it's how often. And so for electromagnetic radiation, the time unit that we use is per second. We say, how many times does it happen per second? And so you may have heard the unit hertz before in your life, especially with computers, gigahertz, megahertz, things like that. This is not the car company. But a hertz is literally how many times per second. Okay, so on the electromagnetic radiation scale, the only thing that we can see is this visible light spectrum. And so maybe when you were younger in science, you learned the mnemonic Roy G. Biv to describe the different colors of the visible light spectrum that we can see. So these are the red, orange, yellow, green, blue, indigo, and violet. But if you look at the whole spectrum, this is a very small portion of what we can see. And you can see to the red side of your visible light, we get infrared. And then we move on to microwave and radio wave. And then on the violet side, on the V side of the electromagnetic spectrum, we end up at ultraviolet and then X-ray and gamma ray. So these on the right side, these are very high energy. And these are bad for us as humans. They start messing with our cells. And then these are very low energy on the red side, and these are all around us all the time. So the fact that our cell phones work, televisions work, our radios work, those are all the low energy electromagnetic radiation. Something that you may want to know on the scale of what we can see, red radiation, red light, has a wavelength of roughly 700 nanometers, and violet is roughly 400 nanometers. So in the entire spectrum, we can see roughly a 300 nanometer scale. And if you look at the whole scale, it spans huge quantities of wavelengths, and we can see a very small range. Okay, so in science, we give these variables, these wavelengths and frequency, we give them variables we can use in equations, and we have several equations. So wavelength is given the Greek letter lambda, looks like an upside down Y. That's the variable that we use, and it's just the distance on any wave to the same point on the next wave. And we use lots of different units for it. For visible light, we use nanometers, as I just explained, but lots of different distance units. And then frequency is actually given the Greek letter nu. It looks kind of like a V to us, but it's given a Greek letter nu. So sometimes in science they also use an F, which makes more sense to us because frequency starts with an F, but I wanted you to be familiar with both. And so frequency gets expressed in seconds to the -1, which means seconds on the bottom. Negative exponents just mean put it on the bottom, which we also call a hertz. So frequency and wavelength are inversely related, which means as one goes up, the other one goes down. Okay, and so we have come up with an equation for this, that the product, so when you multiply wavelength and frequency for all kinds of radiation, no matter what, it's always equal to a constant, and this constant is the speed of light, which we gave the variable c, and you may have remembered that from Einstein's famous equation, E equals mc squared, that c is the speed of light. So c is a constant, and it has a value of 3 times 10 to the 8 meters per second. So sometimes you'll see that in different sources, 2.99 something to many more decimal places. We're just going to leave it as 3 times 10 to the 8th for our purposes. So the equation that we're going to use for the next couple of examples is c equals lambda nu, or we'll use F for frequency instead. So those are the same equation. But C is just a constant, just like R was in our PV equals nRT. So we're going to use that. The one caveat to that is, remember with the R, we had to match the units to it. And so for C, we have to match our units. So we have to be using meters for our wavelength. And then we have to be using seconds on the bottom for our frequency, which we are going to. But it's the meters that gets expressed in so many different ways. So we're just going to try some examples. So it asks us to find the frequency of blue light that has a wavelength of 400 nanometers. So if we're going to find the frequency, we're going to go ahead and use F for frequency. We're looking for the F, and so C is our constant, that's 3 times 10 to the 8th meters per second, and they gave us the wavelength is 400 nanometers. So we're going to plug into this equation, but we have a little bit of a problem here, that our wavelength is in nanometers and we need it to be in meters so that we can match our C. And so we have to convert our nanometers to meters. So we go back to the beginning of the year, and the conversion 1 times 10 to the 9th nanometers is 1 meter. So we do 1 times 10 to the 9th nanometers is 1 meter, and we get 4 times 10 to the -7th meters. And once we're there, we can just plug into the equation. 3 times 10 to the 8th equals 4 times 10 to the -7th, and then times our frequency. So to solve that, you would divide both sides by 4 times 10 to the -7th. And when we get our frequency and we go to 1 sig fig, like is shown here, we would get 8 times 10 to the 14th. And then the units would be 1 over seconds, or seconds to the -1, or we can just write Hz. Okay. So to show you how those units work out in an actual calculation, this was our C, and what we ended up doing was dividing it by 4 times 10 to the -7th meters. That's the math that's actually sitting down here. And so when you do that, the meters cancel out and all we're left with is seconds on the bottom. So that's how that works in that formula. So there's our answer. So we're going to try it again. So question number 2 asks us to find the wavelength of light. So this time we're looking for the lambda that has a frequency of 1.5 times 10 to the 15th seconds to the -1, or hertz. Alright, so this time we know F is 1.5 times 10 to the 15th, and we know C is 3 times 10 to the 8th meters per second. And so we're going to go ahead and plug it in. We don't have any problems with our units. And we'll go ahead and divide over. And when we do that, we get 2, and then since we're going to have to do sig figs, we had 3 up here, 2.00 times 10 to the -7th, and the units here would be meters. Okay, just to show you what we did, we had 3 times 10 to the 8th meters per second, and we divided it by 1.5 times 10 to the 15th. And then since the seconds were the inverse seconds here, they would pop to the top in our division, and that's how we end up with meters. Okay, so this is our frequency, or our wavelength, I'm sorry. This is our wavelength. If you are asked ever if you can see that kind of light, what you'd have to do is convert it to our nanometers, because we know the range of light that we can see is 400 to 700 nanometers. If you convert this to nanometers, it's 200 nanometers, which means it would be on the ultraviolet scale, and we wouldn't be able to see it with our eyes. Okay. All right, and the last one, we're finding the frequency of television waves that have a wavelength of 37 millimeters. So we don't see television waves, and that's definitely not in our range of 400 to 700. So again, we have a problem. We need to go to meters for our wavelength. So we have 1,000 millimeters is 1 meter. So you get 3.7 times 10 to the negative second for your wavelength. And then we're going to plug in 3 times 10 to the 8th equals 3.7 times 10 to the negative 2 times our frequency. So it's the same math over and over and over, just depends on what variable you're solving for. So your frequency, you end up with 8.1 times 10 to the 9th, and the units would be seconds to the negative first, or 1 over seconds, or hertz. Alright, so that's a pretty simple formula. So we're going to learn several other formulas, and this gets used a lot more in physics. So you're going to learn some different things that we've discovered in the last 100 years or so. So next up is, I think he was a German scientist, Max Planck. He discovered that when an object gives off or takes in energy, it does so in certain quantities. And he called those little packets of energy, he called them a quantum. And then he described their energy with a formula, a mathematical formula. So I do want to go over a couple of things in this formula. So delta, the Greek letter delta, means change. So he's saying the change in energy when you absorb energy or you release energy, it's going to have somehow changed. So we give off energy and we take in energy with our food and burning calories. So he said the change in energy is equal to h times nu, or you can use the F for frequency. So what this h is another constant. There's going to be several constants in this unit, and it has this value right here, 6.626 times 10 to the negative 34th joules times second. So our formula that we're going to use to figure out the change in energy is h times frequency. And you see off to the right there's another version of this, because from our last formula we can actually solve for frequency, and we did several times. Frequency is c divided by lambda. Well, you can modify this formula just slightly by substituting in for frequency here, and you can make this formula h times c over lambda, which is what this formula version is. So depending on whether you're given the frequency or the wavelength, you can calculate the energy change. When these little packets of energy are in the visible light spectrum, so the light spectrum we can see, they're called photons. So you may have heard of photons before, but this is what we're talking about, is the energy in these photons. So we're going to practice calculating just a couple of these. So we're going to calculate the energy of the red light change that would happen when it has a frequency of 0.85 times 10 to the 15th. So our formula is delta E equals h, which is 6.626 times 10 to the negative 34th, and it's joules times seconds. And we just simply have to multiply it by our frequency, which is 0.85 times 10 to the 15th. And hertz, remember, is 1 over seconds. So if you look at your units here, the seconds are actually going to cancel out, and you're going to end up with just joules. So your change in energy for this thing is 5.6 times 10 to the negative 19th joules. Okay, and so what this energy is calculated as is joules per one little photon. So that's a tiny amount of energy, but that's per photon, and usually when light hits you, there's a lot of photons there. Okay, so we're going to try it with the modification of how do you determine the energy if they give you the wavelength instead. So we talked about a modification of that formula, which you don't have to do. You could go use the formula separately and then plug in, but we're going to try this one. And so one little issue with this is this wavelength is in nanometers, and all of these formulas, because of the C, require it to be in meters. So I'm going to do this all at once, and you can do it in different steps, but I'm going to do the conversion all at once, just to show you that you can put them all together. So I'm going to put my H, which is Planck's constant, 6.626 times 10 to the negative 34th. And then I'm going to multiply it by my C, which is 3 times 10 to the 8th meters per second. And then I'm supposed to divide it by my wavelength, which is 10 nanometers. And so right now you can see the seconds cancel out, but the meters and the nanometers don't. And so usually we convert separately, but you can put that conversion in with nanometers and meters that we talked about. 1 times 10 to the 9th nanometers equals 1 meter. You can put that in here, and so the 1 times 10 to the 9th would have to go on the top, so nanometers cancels out. And the 1 meter would have to go on the bottom. And if you look what happens with the meters, they cancel, and the nanometers cancel, and you end up with just joules again. So you don't have to do it like this. You can do it in pieces, but some of you may prefer this. This is a little cleaner. So you get your delta E to be 1.98, so I should round it to 2.0 times 10 to the negative 17 joules. All right, and then the last one of these, just to solve for it from a different perspective, it has to determine the wavelength that has an energy of 6.2 times 10 to the negative 19th. So I'm going to actually work this in multiple formula steps so that you can see it different from what I did in the earlier question. So this time, I'm going to go ahead and use this formula first. I have the energy, so I'm going to plug that in, 6.2 times 10 to the negative 19th joules. And I have Planck's constant, so 6.626 times 10 to the negative 34th, and joules times seconds. And I don't have frequency. So to solve for that, I'm going to simply divide. And I get my frequency is 9.4 times 10 to the 14th, and that would be 1 over seconds or hertz. The joules would end up canceling, and you would end up with seconds on the bottom. But I was asked for wavelength, so then I'm going to plug into C equals lambda times frequency, and do 3.0 times 10 to the 8 meters per second equals lambda times 9.4 times 10 to the 14th. And I'm going to keep that answer in my calculator from before. So even though I wrote down 9.4, I'm using what's in my calculator. And get my wavelength is 3.2 times 10 to the negative 7th, and that would be in meters. Okay, and then things that they can do with that is also ask you, can you see it? And you don't have to do this on this question, it wasn't asked. But if you did convert that to nanometers, it would be 320 nanometers, which would again be in the ultraviolet portion of the spectrum, and we wouldn't be able to see it. Okay, so next up, we're going to talk a little bit about how we view the atom now. So in the early 1900s, we had what was called the Bohr model. And so when we talked about developing the atom earlier this year. Once we discovered the nucleus, Niels Bohr proposed that the electrons traveled around the nucleus in little orbits, like planets do around the sun. And so we came up with some new definitions based on these little orbits. We called the different orbits energy levels. And so depending on how far away from the nucleus you were orbiting, we had energy level number 1, that was the closest, and then energy level number 2 and 3, and so on and so forth, where the further out you got, they were called increasing energy orbits. And so now we know that, or we don't use orbits for locating the electrons, but we still use these designations for some calculations. And so unfortunately, you'll notice that we reuse the same variables for multiple things. The energy levels, or these orbit levels, they use the variable n to refer to the energy level. And so we already use n for moles, but we also are going to use n for energy levels. And they don't often get confused because we're not at all using moles when we're talking about the individual atom. And so when we're talking about moles of things, we're not talking about the individual atoms, so we don't use energy levels. So, but the idea is that if you're going to move an electron, let's say, from this energy level, this first energy level, and you're going to pull it out, let's say, to the energy level number 3, you're fighting its attraction to the nucleus. So you're going to have to put in energy to get that to pull out away from the nucleus. So to pull out that electron, the atom's going to have to absorb energy. You're going to have to go give it energy. It's going to have to take in that energy. But then when the electron falls back in, when you stop providing that energy and it falls back to that first energy level where it belongs, think about a spring, okay, that energy that it took in is going to be emitted right back out. And we can actually calculate the energy of this light that gets calculated, or that's spit back out. We just talked about calculating energy. And then depending on its wavelength, we may see it as a color coming out of it. So one of the labs we were going to do was to try to give energy to different atoms based on, or using fire, and then watching the colors that came back out when that energy was released back to us. And so that's what happens in fireworks. And so since we won't get to do it this year, we will definitely try to do it next year because it's actually one of our more fun labs. But for right now, we're going to see if we can calculate this energy. Okay, so there is another formula, there's lots of formulas here, that said the energy of a particular orbit with an energy level n and nuclear charge Z is given by this formula. So we're going to talk about what this Z is in just a second. But if you pick any particular energy level, okay, and you wanted to calculate the energy of it, this is the formula you would use. So n is the energy level, and you'd have to be given a specific energy level to look at. But then Z is called the nuclear charge, and what's in the nucleus that has a charge is protons. So all Z is the number of protons. And this is pretty simple because this we can get from the periodic table. Every element has a different number of protons. And so this one's going to be a kind of involved calculation, and then we're going to learn a shortcut for it that someone put together. So it says, can you calculate the energy of light associated with an electron moving from the second to the fourth energy level in a hydrogen atom? So when they tell us it's a hydrogen atom, we know that the number of protons is 1. And so there are two things that we're going to have to do here. We're going to have to determine the energy of level 2, and then we're also going to have to determine the energy of level 4, and then figure out the energy change that goes between those. So for energy level number 2, we're going to put negative 2.178 times 10 to the negative 18th. And then we're going to put our Z squared, which is our 1 squared, and over our energy level squared. So since we're dealing with energy level number 2, put a 2 squared in there. Okay, so I'm going to calculate that. Okay. So I get the energy of level 2 to be negative 5.445 times 10 to the negative 19th joules. I'm going to repeat the process for 4, and so since it's that same atom, all I'm going to do is change the number of the energy level. So I'm going to have 4 squared down here. So when I calculate this, I'm going to get the energy of level 4 to be negative 1.361 times 10 to the negative 19th joules. Okay, but we want to know the energy change that happens with going from the second to the fourth energy level. So when we do a delta, that's what change is. We do change in energy. whenever we do delta, we always do final minus initial. So the final was the fourth, and we're going to subtract the initial, which is the second. So we're going to take negative 1.361 times 10 to the negative 19th and subtract negative 5.445 times 10 to the negative 19th. So our delta E is 4.08 times 10 to the negative 19th. And that would be in joules. All right, so that was a little long-winded. Then you could, if you were asked, you weren't asked here, but you could go use that formula we talked about earlier, and you could go solve for the wavelength of this light. So I'm going to do that just really quickly because I wanted to talk about the color that you would see. And so if you use that formula and went through all that stuff we had done before, you get 4.86 times 10 to the negative 7th meters, or 486 nanometers, which from what we've talked about is definitely part of our visible spectrum. So when the electron would go from 2 to 4, we would have to put in the energy to make it go up. But then when it fell back to where it belonged, back to the second, it would give us back this energy, but we would see it as a color of light. We would most likely see it as a bluish light coming back to us. So when atoms emit colors of light, that's what they're doing, is the electrons are changing energy levels. So what we have discovered is that every element emits a different kind of, or different pattern of light based on its electrons, because every element has a different set of electrons. So everything has its own unique spectra. And this is how we figured out what elements are in the different things in space. Like what elements are in our sun, what elements are on Mars, what elements are on Venus. And in different stars, we look at the spectrums that come back to us and compare that to the known spectrums of elements that we recognize on Earth, and we match them. And so that's how we figure things out. We use spectroscopy, and it's just looking at the spectrums that come from the different light. So that was a little long-winded, but there is a combination of what I just did with all these equations with the delta E and the energy formula to go figure out this wavelength in what's called the Rydberg equation. So it goes directly to wavelength from the difference in energy levels. So this is just a combination of the things that I just showed you. So in this formula, N1 and N2 are the two different energy levels that you're dealing with. And so for wavelength always needs to be a positive number. And you notice there were some negatives in that last formula. And so to get this to always be a positive number, you need to put the smaller energy level first in this N1 and the bigger energy level second. If you forget to do that, what you can also do is use a mathematical construct called absolute values. And whatever you get out of here, you just make that positive. Okay? R here is not the R that we learned from gases. It's called the Rydberg constant. And it's 1.096776 times 10 to the 7th meters to the negative first. Okay? And so we're going to use this to calculate an energy change like we just did. So we're going to get that same answer here, hopefully, if we do it right. It says calculate the wavelength of an electron in a hydrogen atom going from level 4 to level 2. So that's what we just did. But we're going to do it directly into this equation. So we get 1 over lambda equals R, which is, if we go back, we get 1.096776 times 10 to the 7th. Okay, and then we have 1 over, and we're supposed to put the smaller one first. So 2 squared minus 1 over 4 squared. Okay, and so what the Rydberg constant does is merge all those other constants that we've been using together. So if I calculate this, the first thing I'm going to do is calculate the parentheses, and then I'm going to multiply it by R. Okay, so what I get here is I get 1 over lambda equals 2056455. But to solve for lambda here, I'm going to have to multiply lambda up, and then I'm going to have to divide that number back down. So essentially, I'm just doing the reciprocal of that number. So if I do that, I get my wavelength is 4.86 times 10 to the negative 7th, and this would be in meters. Okay, so this is the exact same answer that I went through and got right up here, but a lot less work. So the Rydberg equation just combines all these formulas together into one, and it just requires that you use a different constant, this Rydberg constant. Okay, so we're going to practice one more of these, and then we'll be done. So this one asks us to calculate the frequency, so this one's a little trickier, of the radiation emitted by a hydrogen atom with a transition from 3 to 2. So we're going to start off with the Rydberg equation, okay, using that same constant. And then we're going to have 1 over, and we're going to do our smaller one first so that we get a positive. All right, so I'm going to work the parentheses first, and then multiply it by our Rydberg constant. So I get 1 over wavelength is 1523300. But that's not wavelength, so I'm going to have to do the reciprocal. And I get my wavelength is 6.56 times 10 to the negative 7th meters. But the tricky part of this one is it asks for the frequency. So I do have an equation that goes between frequency and wavelength. So I'm going to pop that one in. And solve for frequency. So I get my frequency is 4.57 times 10 to the 14th. And that would be 1 over seconds or hertz, based on what we did before. And I wouldn't do any sig figs on this because the energy levels really don't have significant figures. Okay, so lots of equations. We'll learn a couple more this unit, but that's the majority of the math.